We spend a lot of time learning MIG and TIG and all those things that for some of you might have been very new concepts, right? Like we had to learn a dictionary. Then we talked a little bit about metallurgy, right? That should have been a refresher. And then we got into like the foundations of welding, especially of arc welding that is so used. And I talked about the welding arc, right? And we talked about all this physics of the arc and all this crazy stuff. But the bottom line is that there is some voltage associated with the electrodes, right? And intuitively, we did a bunch of things like saying, okay, this would change penetration or deposition rate. But right now, as of today, you know how to calculate, to estimate a voltage in pretty much any arc welding process, right? And that in itself is very powerful. What I want to do today is to say, well, voltage times current is energy. So let's do a mass and energy balance, and we're going to be able to calculate the deposition rate in welding. And this is extremely important because it's at the core of the economics of welding. People will sell you a product like metal core because it has higher deposition rate. Right? The people measure the productivity of welders by how many pounds an hour they put. And so this concept is all based on those voltages that come from the plasma and these particular features of the plasma near the electrodes. And we apply them to the mass and energy balance. So I showed you last class this energy balance here, which is the same we would have done in our heat transfer class. And we said, okay, heat comes in, it comes in, goes out, is generated, is stored. So heat comes in by the fall voltage on the electrode. That can be an anode or a cathode, depends on the polarity. That's why I call it just fall, right? But typically MIG or subarc welding is an anode. Q from the arc to the droplet, which I'm going to show you later, but I'm going to forget about that. I know how to calculate it, but it's not a big deal. And there is heat from the contact tip in this point of contact, electrical contact at the very edge of the contact tip, right? That generates some heat. I'm not too sure how it's split. Some goes into the wire, some goes into a contact tip. I'm going to say it all goes to the electrode. It's small enough that we shouldn't worry much about it. That's in. How does the heat go out? Well, the droplet evaporates, right? And I mentioned the fumes, right? And you got to see these fumes. And again, I'll tell you in a couple of slides from here, I'm going to say that's very small. But evaporation actually matters. From the point of view of an energy balance, I don't see it playing a significant role, at least at this stage of our teaching. Heat generated is the heat generated by Joule heating, right? And I mentioned this formula you will have in your formula sheet, but it is something simple enough that I hope you would remember forever, right? That resistance is resistivity, which is a material property, times length divided by the area. And then the heat is stored in the form of enthalpy. Right? We start with cold wire, we end up with hot wire. Right? The heat is stored there. And you already had your classes on thermodynamics. I'm going to go over the details, but you know that. So let's get in, start with the heat input. So the heat input we say is the fall plus the arc plus the contact tip. I said I'm going to forget about the Q of the arc, and the heat of the fall is voltage times current. And these numbers are numbers you do not need to remember by heart. But you would know that the anode is some voltage, of 5 volts, 4, depends if it is aluminum. If it is a non-thermionic cathode, it's much higher, it's almost 14 volts. Right? And if it is thermionic cathode, it's another story. So we know all these voltages, what we would put here. Q that comes from the arc is more or less 1% of the energy balance in typical cases. let's forget about it because we have our hands full with what we're learning now. And Q, heat that comes from the contact tip, is resistivity of the contact tip times current squared, right? These are the formulas which will not be on your formula sheet. This will not be on the formula sheet. Voltage, current times resistivity, right? And so we have a power is voltage times current, or I square R. You can also say V square over R, right? It's all the trivial substitutions. So this is called Ohm's law. Okay. So with that, I'm using this. And the resistance of the contact tip depends on many things. And I mentioned to you how like the surface finish of the electrode has a very important influence on this. For this class, we're going to call it 2 milliohms, right? Which is a realistic number. Although sometimes it's 1 milliohm, sometimes it's more, depends on if whether the contact tip is worn out or not. But with 2 milliohms, we get reasonable numbers. This is a heat that comes into melting our wire. We said that Q out is the mass that gets evaporated times the enthalpy of evaporation. I'm going to call it 0 so we don't need to fret about this. And there is nothing tricky about that. But there is evaporation. There is. I believe evaporation determines the droplet temperature. I don't know exactly how yet. But there is enough evidence to indicate that. Heat generated by Joule heating. So this heat generated is I squared times R, and this is the resistance. You will have this formula. Resistance is length times resistivity over area. This effective resistivity is a material property. Now, the resistivity depends on the temperature. And in the electrode, you start with the electrode at room temperature and you finish with the electrode at melting temperature. So in all that range, resistivity is changing by almost an order of magnitude in the case of steels. So which resistivity should you pick, right? Well, in reality, what you have to do is the integral, and it's a very complex integral. It's an integral we have done, we have published, and we know how to handle. But if you do that integral, and then you do you say, okay, what would be, if I were to assign a constant value that gives me the same value of the integral, some sort of an average, you would be using a number like this for steel, or numbers like this for aluminum. I want to draw your attention. Aluminum is more or less resistive than steel. Less is here, and you also know, right? Aluminum is a good electrical conductor. At one point when there was a scarcity of copper, people made wiring with aluminum. Some of the really old houses here in Edmonton have aluminum wiring. It's fire hazard because it's not as good as copper by a long shot. So by Joule heating, those wires generate heat that can end up in unhappy situations. Okay, so because you have these values which will be in your formula sheet, you now can calculate the heat generated by the electrode. So look at this. These, which in the end we are going to be calculating, you see these curves? They were done, I think these curves come from the 70s. They were done at Lincoln, and I believe somebody measured, and then another guy came with a curve tracer and went over. I don't think these curves are all too exact, but this is what is in every catalog. If you buy electrodes from Lincoln, the way you would say what wire feed speed and what current, how wire feed speed and current go together would be from using this figure, this exact same figure I'm showing you here. And what do you see? Here you have different wires. So let's start talking about just one of the features. You see all these are kind of banana curves, right? What happens? Well, at the beginning, at low currents, Joule heating is relatively small, so the anode fault voltage takes care of most of the heating. So that is the heat in that case is voltage times current. Voltage is the default voltage is constant and gives us a line. But when the current is high, it goes with I squared, right? And with current squared. And that's where you have this part of the curve that bends. What this is showing, that Joule heating starts to be more and more relevant. So now it's interesting because as I increase my current, my deposition increases more than proportionally. But penetration increases more or less proportionally. So I would be changing my dilution, for example, in cases like this. Right? It's not true that if you increase the current, everything melts more equally. Right? This is an interesting thing. Here, this part of the curve, the Joule heating is very small, and this part of the curve, when it's bending, increases quite a bit, the Joule heating. And another thing, and I'm showing you these curves, but then you'll know how to do this yourself. Imagine I increase my electrode stick out, right? Remember the stick out, the amount of wire that's sticking out outside of the contact tip? The resistivity of the stick out would increase or decrease if the stick out is longer. Would increase, right? This is the formula that I hope you'll remember, that resistance is proportional to the length. Now, if my resistance increases at a given current, right, am I generating more or less Joule heating? More Joule heating, right? Therefore, with more stick out, I should melt more wire. Okay, check it out. Here they have this, let's compare this. 532 wire, this is for submerged arc welding. 532 wire here, 532 wire here. This has 1.5 inch stick out. Here you have 2 3/4 stick out. It's longer, and you see the deposition rate in pounds an hour went up. If you look at this 332 wire here and there, here you have 1 inch stick out. In sub-arc welding, right, everything is bigger. And here you have 2 1/4 stick out, you have more deposition rate. Right? It's Joule heating what's making the difference. I'm a big fan of, this is called extended stick out, right? I'm a big fan of extended stick out. Somehow it's not very common in industry. So far, nobody gave me a very good reason. But I can tell you something. Imagine you have your normal MIG machine and you want to have a longer stick out. Have two problems. One is if the stick out is too long, shielding might be difficult, right? Okay, but we can deal with that. The other problem is, remember when we talked about cast and helix of the wire? The wire is rolled. So if you have too long of a stick out, the wire comes a little bit bent. So as the welder is welding, it's going to see that the wire is wandering all around. And if it is an automated process, that's a big problem, right? So people don't have very long stick outs for that reason, the cast of the wire. Now, there are ways of solving this. For example, you can have you can have an electrical stick out and a mechanical stick out. In the case of hot wire, you have something like that. For example, if this is your wire, you could have this. This would be an insulating tube. And here you can have your copper contact tip. So now you would have an electrical stick out that goes from here to here, right? That's your electrical stick out. However, your mechanical stick out, the one that can give you problems, would be only this, right? And this is That's what they are doing in this case for submerged arc welding. This could be done in MIG too. I don't know why they don't do it. And I ask. I never get a straight answer. If you do this, you'd have a lot more deposition. Now, here's the catch. You can put a lot of wire with low current, but then you might have penetration problems, right? So there's always a balance of things. All right. More stick out gives you more deposition rate. And you know this by intuition. I want to form your intuition before we do any formulas. So there's another thing. This is the cross-section of a MIG wire. This is a cross-section of a metal core wire. If I have two wires of the same outer diameter, they look the same to you. Which one would have a higher resistance? Metal core or MIG wire? Metal core, right? Because the cross-sectional area is smaller. Resistance is higher. If resistance is higher, I'm going to be generating more joule heating, right? And if I generate more joule heating, then with the machine at the same current, I would be depositing more metal for the same amount of current. So these curves that I'll explain to you in a second, they all come from experimental data from ESAB that they publish, right? And let's look at the 045 wire. Is this green one here? Okay, let's look at this yellow one. Sorry, this is the 045 wire, right? This is MIG, and it says as current in the vertical axis we have pounds per hour for 100 amps, right? And we'll see why this matters. But the pound per hour is how you measure your welder. And per 100 amps, because obviously if I put more amps, I'm going to put more pounds per hour, right? So for 045 wire, we oscillate here around, this is around 3, right? But if we use metal core, then we increase by 20%, right? For the same amounts of amps, we can put 20% more metal. That's one of the arguments with which people sell you metal core wires, the higher productivity. There are other advantages too, right? So we're going to come back to this concept of the burn off and the pounds per hour per 100 amps. My point here is when we do an energy balance, and the energy balance has different sources of heat, joule heating has a significant effect. The stick out matters, the wire diameter matters, or the cross section here matters. Okay, I forgot to mention here. Look for this is a thick wire. This is a thin wire, right? Well, let's worry about that later because there are other reasons there too. So we talked about heat in. We talked about heat out. We talked about heat generated. And before I move too far, what are the sources of heat generated in the wire? What is the source of heat generated in the wire? Resistance heating, right? Joule heating. What heat comes into the wire from outside the control volume? What would that be? The heat from the fall voltage, right? And from the contact tip, those two. There are more things, but we said let's forget. How much heat gets out of the electrode? Let's call it 0 right now. Evaporation is the largest, and even that in the whole balance is very small. So we're going to forget about it. So we have two things coming in, one thing being generated, and the heat is being stored in the form of enthalpy. So if you do thermocalc or those packages, thermodynamic computational thermodynamics package, so you can graph the enthalpy, that is the amount of heat in the wire material takes as a function of temperature. Let's say we start at 20 degrees, right? And we end up at 2500 degrees. Okay, still at 20 degrees, what's the state? solid, right? 2500 degrees, liquid. Okay, so what do you think this big jump in enthalpy is? Yeah, they change from solid to liquid, right? So this line here is the solidus, this is the liquidus, and this jump here is the latent heat. Good? Okay. What do you think? We were having a happy line here, and then we have kind of a little bump. What is this bump? Which one? Correct, right? That's what's happening. So that, and you see it's not all that big. So in welding, you start at 20 degrees, give or take. You finish, the droplet is at 2500 degrees in steel, give or take, right? And I know this because we measured it. So what I'm going to propose is to calculate the amount of heat stored in our wire, is to do this. We want to have the enthalpy of the droplet minus the enthalpy at the beginning. And I'm going to say, let's go from 20 to 2500, right? And that's what I call my enthalpy of reference. I get it from thermocalc, and that is fairly accurate, right? And that accounts for the transformation from ferrite to austenite, accounts for the latent heat of melting, accounts for the specific heat, right? That accounts for everything from 20 to 2500. And then I'm going to say, well, the droplet might be a little bit hotter, might be a little bit colder. So I'm going to account for this specific heat of the droplet as it varies here. When we do the formulas, you're going to be doing yourself, so you'll get the process memory of this. Do you remember seeing this in thermodynamics? Do you remember more or less? Oh God. When I talk to my colleagues, they say you guys are ready to do quantum mechanics computations, but I'm not too sure. But something like this, you have to see. Remember the concept of specific heat? Okay, that's the slope of this curve. Hey, those of you who took heat transfer with me, you know this one. Okay, thank you. So then, of course, I should make another compensation at room temperature. But look, the droplet might vary by hundreds of degrees. If it is hot, we'll go from 20 to 30 degrees. If it is cold, might go from 20 to minus 20, right? If we want, we can account for that. For the sake of this class right now, I'm going to account only for what happens with the droplet. Okay, but we can go and do anything else we want. We can account for variations. What happens if you weld in Saudi Arabia versus if you weld in the North Pole? We can account for all that. So this is kind of an approximate formula that takes us from 20 degrees to anywhere in the droplet and comes from thermodynamics. All right, so because we did thermocalc for the case of steels, and we forgot to put the units here. This is joules per kilogram here and joules per kilogram here. I have it for steel and for aluminum. Now, here's the beauty of this approach we're doing. Yes, steel and yes, aluminum, and that's what everybody uses. But if tomorrow you say, I want to try the welding of tantalum, say for whatever reason you want to do MIG welding, I would go to thermocalc and ask thermocalc the enthalpy of tantalum, and I'm giving you this value, right? In any case, you should not do MIG of tantalum, huh? But there can be crazy materials, and with this approach, you can start anticipating things. All right, and what is the droplet temperature? These are old measurements. We have newer measurements that are better, but I mean the process of processing them. So this was a student who did his PhD with me when I was still in Colorado. Look at this super interesting thing. This is current. This is droplet temperature. Here we have And do you see in all cases we have this kind of dip here? Do you see this is carbon steel, this is aluminum, this is stainless steel, and this is carbon steel with different amounts of CO2. Do you see like a common thread, like there is like this dip, right? Okay, this dip here is right at the transition current. Remember when we go from globular to spray? For reasons nobody understands, I don't, but we would love to eventually figure out, there is a temperature minimum right at the transition. In globular, you have like a little bit of a hump. It gets hot, 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 and then goes down, and then in spray transfer goes up, 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 and then saturates. Right? And this saturation is at a temperature close to the boiling temperature of your alloy, or boiling temperature of your components. So for example, if you have pure aluminum, it's high. So if they're 2500 C. But if you have aluminum with magnesium, magnesium has a lower boiling point, and it lowers the boiling point of the droplet. Right? It's a very, very interesting thing. So, but what matters is, look, when I said that the droplet is more or less 2500 degrees, yeah, it's what comes from this graph. In spray transfer, this is more or less 2500. Here you would have 2500. So it's, this is old. For aluminum, we're measuring lower temperatures now. Let's call them 2000, right? So this is how droplet temperature goes. And I'm going to call it 2500 C for the sake of most examples. Now, if I put all this together, I would have heat in minus heat out plus heat generated equals heat stored, right? This is wire feed speed times linear mass of the wire times the enthalpy, right? These together are kilograms per second times the enthalpy, right? All I did is to go from our equation number 1 from heat transfer. I put all the Q ins and Q outs, and I got this. Now I can solve for wire feed speed. You see, it's the wire feed speed. And I get this formula. This formula will be in your formula sheet. Now, this formula is so extremely powerful. This formula says so many things. Before I let it speak for itself, I'm going to go over some of these things here. Look, it says wire feed speed increases with the fall voltage. Right there, you would know things we have been discussing a lot from intuition. If I flip the polarity and I go from electrode positive with a 4.8 volt anode fall to an electrode negative that becomes a non-thermionic cathode at 13.8 volts, I go from 4.8 to 13.8 here, the wire feed speed is going to increase. You knew that. Everybody knows that. They just don't know why, right? And if I do any type of variable polarity, and I would get an average here. Here we have resistance of the stick out. If I increase the length of my stick out, I have more resistance. If I decrease the area, I have more resistance. Those are the things we have already discussed many, many, many times. But I'm hoping to make them become intuitive. And you see, this was proportional to current, and this is proportional to current square. So in our curve that looks like a banana, this is what makes it like a banana. Now, I don't have a slide for that, but I have uploaded the notes for, in the MIG guide for Lincoln, they have the same curves for aluminum. Question to you, do you think aluminum is going to give us like banana curves or more straight curves in wire feed speed versus current? It's more straight curves because the stick out doesn't matter very much in aluminum, right? Isn't this quite amazing? Down here I have the linear density, the linear mass of the wire, how many kilograms per meter. And here I have my enthalpy, that is a reference. And here I have specific heat and droplet temperature. If I have a hotter droplet, question to you, if I have a hotter droplet, for whatever reason, do you expect more wire feed speed or less wire feed speed?
Less wire speed.
Hotter droplet is less wire feed speed, right? It's dividing, right? And it makes sense because they take more energy. So, for example, when we go through these variations in temperature, right, we actually see a change in wire feed speed. In these curves I showed you from Lincoln from the 70s, they just put a curve tracer because it's a subtle change. But you get to see those things, right? Some people actually have solved this for droplet temperature, assuming they know everything else, then you can solve for droplet temperature. If you measure wire feed speed and you measure current, if you know your fault voltage, you can solve for droplet temperature. I think it's a risky measure, but you can. All right. If you get that exact formula, this formula here that will be in your formula sheet, and you put the values that we have been discussing all along, the 4.8 volt full voltage for steel, 2 milliohms for contact tip, right? All these things that will be in your formula sheet, all tabulated, what you get is this. The dots are the measures from the Lincoln catalog. Those are the curves I showed you at the beginning that I told you they made them in the 70s with a curve tracer. These dots are what people put in the catalog. The lines are the formula I gave you. As you get to see, this formula is quite awesome. Is it perfect? No. Now, if you ask me who's not perfect, my formula or the measurements, I think it's an even battle. I don't know. But what I can tell you is the measurements, I'm sure they're not horrible, and the formula is for sure not horrible. You in your exam, you will be able to calculate things that nobody else can calculate. And you can answer many important questions I answer for you. So this is a formula with the values you have tabulated. No fudge factor, no correction factor, no nothing else. The things we've been discussing since we started to talk about arc. There's another concept, the concept of burn off or melt off, right? How many pounds an hour does the welder burn, right? Or does your machine, can your machine do? And this is pounds an hours, right? And it's wire feed speed times the linear density of the wire, right? That's very simple. And because we have a formula, we would get this. Now, if we look at pounds an hour per amp, per 100 amps, remember I mentioned this concept, we would have this, if we go to what we have, to this formula, if we go to this formula, right, and we divide by current here, divide by current there, we get full voltage divided the enthalpy variation, right? That is more or less the enthalpy reference. This is a constant, more or less constant. The droplet temperature can change a bit, but this enthalpy is more or less constant. Full voltage, more or less constant. Length of stick out, more or less constant, right? Effective resistivity, more or less constant for a material. The enthalpy is more or less constant. And here we have current divided the cross-section of your wire. Okay, that is not constant. For a given wire, you can have any current you want. Now, what happens, and this is something for which I need to ask the practitioners, but in practice, this current per cross-sectional area of the wire is more or less 2.2 times 10 to the 8. So this is 220 amps per square millimeter. 220 amps per square millimeter, give or take. When you want to put too many amps in a thin wire, people would say, no. Let's put those many amps on a thicker wire, right? So in the end, you don't go with crazy high currents in crazy thin electrodes. You can if you want. For reasons I don't know, you never want. You stay close to this type of 220 amps per square millimeter. So this is more or less constant. So all this is more or less constant. Here we have resistivity of the contact tip times current and with reference enthalpy. This is not constant. That depends on current. But again, resistance of the contact tip is relatively small, right? And if you do this calculation, that it gives you this is a constant with something that is a small variation, you are going to end up calculating a number that is equivalent to 2.7 pounds an hour per 100 amps. Remember I showed you before it was like 3, right? From these ESAB experimental curves. So I still have to do some more harmonization, and that's how every year our numbers change a bit. But this is quite amazing. By doing the absolute fundamental from scratch, right? We built it, and we can say in MIG, you're going to burn more or less 2.7 pounds an hour per 100 amps. That is fantastic, because if you have to do a certain job, now you know how long it's going to take you. If you know what groove you need to fill, you need how many pounds you need. You know how many pounds you need, and then you know how many hours you need, or how many amps you need. You start knowing so many things. Extremely powerful. Now, something that is, I think is so amazing. If you go to the Lincoln Procedure Handbook, to the section in economics of welding, it says, well, to do the economics, we need the deposition rate. And without giving any justification, they say you can approximate the deposition rate as arc voltage times current divided by 1,000. This is in pounds an hour, right? Now, this is the awesome thing. I think the formula is wrong, but it gives you the right number, because arc voltage includes the column voltage, includes the plate voltage. Does a plate voltage melt any more wire? No. The arc voltage? No. The column voltage? No. So when they say this, I don't know, they were kind of thinking very holistically. But if we take this seriously and say, okay, let's do the anode fault voltage plus a 10 millimeter arc length, just to give it a number, that would give us 8 volts and a cathode voltage 13.8, right? And this gives us 26.6 volts, right? These 26.6 volts here, they end up giving us the exact value, 2.7 pounds an hour every 100 amp. That is what we calculated from first principles here, right? So it's incredible how we started talking about the non-local thermodynamic equilibrium of the plasma, and we say 2.7 pounds an hour every 100 volts. And then you have the Lincoln Procedure Handbook, which all of you should have. And it has a section on economics, not on physics, on economics, and say, well, this is a good approximation. I'm never going to tell you why, but this is, I think, is good. And guess what? We're pretty much the same, except that we're better. Because if you increase the arc voltage, you don't melt more wire, right? But we know that, and we can account for that. You guys are powerful. You're going to be dangerous. OK, so this is a formula I just taught you, right? This is just the formula, plain and straight. No correction factors, no fudge factor, no nothing. And this is a formula that gave us these good curves here, or as good as I could get them. All right. So what is the effect of wire diameter? All right. Where is wire diameter in this formula? Where is the wire diameter?
The resistance of this.
That's one. There's another one. That's true.
Enthalpy?
Enthalpy is a material property. So
Um,
here,
yeah.
right, the pounds per, the kilograms per meter of wire, right? So a thicker wire is going to have more. And this is another formula I'm not going to put for you there, right? But the cross-sectional area is pi diameter square over 4. If I multiply that by density, that gives me the kilograms per meter. Right? So the wire diameter appears in these two. So this blue one is my reference. It's an 045 wire. And there's something interesting in the 045 wire. I hate myself for using inches, but here in Canada, everybody, they claim to be metric, but it's not true. They do everything in inches. So the 045 wire, that is a 1.1 or 1.2 millimeter diameter wire, has, if you have 200 amps, has more or less 200 inches per minute. You see this curve, the blue curve? 200 amps, 200 inches per minute. You have 250 amps, more or less 250 inches per minute. So it's kind of convenient because with that 045 wire, I more or less know where we are standing. The other wires, I have no idea. But this one, I do. OK, so if we go to a wire of larger diameter, we should have a lower wire feed speed, right? For two reasons. We have less resistance heating, but even more importantly, right, a bigger wire is going to take more mass, right? Bigger wire takes more mass, so I need to move slower because I cannot melt so much mass. We see that here. And that's the reason why we have this big spread. This is related to the mass of the wire. Thin wires, right? Thin wires have little mass, so you have to feed them very fast. Thick wires have lots of mass, so you feed them slowly. Now, if I have a thin wire that I'm feeding fast, or a fat wire that I'm feeding slow, it's more or less the same, right? More or less the same, but not exactly the same, because the joule heating matters. And that is one of the things you identify. So in this curve here, for the burn-off, in burn-off, where is the wire diameter? In the stick-out. Is there any other wire diameter? No. So this difference here, in which the thicker wire has less productivity, is because it has less resistance heating. So you can get to choose either wire, and you'd be fine. I don't think your company is going to go bankrupt because of this. But you start to understand things, right? If somebody tells you, well, you should use 045 because the wire feed speed is so much faster. Yeah, wait a second. Kind of true, but not completely true, because it moves faster, but it's thinner. But there is a little bit of an advantage. Yes, that is true, a little bit. But you're aware of that. And with this formula you have here, you can calculate this yourselves. And the values that you have tabulated that I gave you. And you can, right there, settle these type of arguments. All right, effect of the stick-out. So here on the left, always have wire feed speed. On the right, we have the burn-off. And on the left, we have, in blue, we have the 045, let's see. The blue is the 045 wire. And with a longer stick-out, we go from half an inch stick-out to a 0.75 inch stick-out, right? 3/4 of an inch. What would be, what is that? Like 20 millimeters, right? 19 millimeters stick-out, from 12 to 19. And what do we expect? Yeah, we would expect faster wire feed speed and more burn-off, more or less the same in this case, right? Because the wire diameter didn't change. Now, if I do this, I have the risk that the cast of the wire starts playing games with me, right? Shielding might be a little bit more difficult. But you start to see already what's happening, right? In this case, the gain is a true gain. With the wire diameter, it's kind of a tricky gain. because the higher wire feed speed is tricking you. But in this case, higher wire feed speed is the same as a higher burn-off, because the wire is the same diameter. All right. Let's talk about the droplet temperature. So if the droplet temperature went from 2500 C to 2800 C, right? It's a hotter droplet for whatever reason. But if you remember, the droplet temperature does change about 300 degrees as we go through different transition periods. And in that case, if the droplet temperature was higher, do you expect faster or slower wire feed speed? Slower, because we are taking more energy in heating the droplet. Sure enough, here you get to see the decrease, right? You see a decrease in wire feed speed that is of the order of, what is that, like about 40 inches per minute, right? It's about 10%, a little bit more than 10% of decrease in productivity. Again, I don't think your company is going to go bankrupt for that 10%. But as you understand this, if you start seeing difference that the wire feed speed and current start to have a funny behavior, you can start asking yourself questions about what's happening with the heat that is transmitted to the wire. Effect of polarity. All right, so if we switch it and we have electrode, we switch it to from electrode positive to electrode negative, right? The full voltage goes from 4.8 to 13.8. Right, I remember that, but it's going to be in the formula sheet. And then all of a sudden, yeah, if your full voltage is so much higher, your deposition rate is so much higher. It's a lot higher. This is awesome for overlays. It's awesome for overlays, but you might have, for example, lack of penetration because you might not be melting enough plate. Also, there is something that, again, I don't fully understand, and I don't think anybody really does. But when the droplet is the anode, the arc is very well concentrated either under the droplet or around the droplet. But when the droplet is a cathode, remember that I showed you these cathode spots that jump all over the place? So the cathode doesn't have a good attachment to the droplet, and the droplet is thrown to the sides, right? So you have like a very kind of like globular transfer that is very unstable. So people typically don't like using electrode negative outright. Yes, variable polarity, but not just electrode negative outright. But look how much more wire you're melting. If I were to give you the problem with variable polarity, right? So this voltage fall would be the average, the weighted average of the voltage falls. All right, metal core. This is trickier to do with the formula just as I gave it to you. So, because you have to account for the mass of the metal that is not conducting electricity. But I did it. And you get to see if you have metal core, you would have a higher wire feed speed. Sure, because you have two reasons. One is you have a higher resistivity, and the other, you're putting less metal because what is inside the tube is not 100% full, it's powder, right? Let's say 60% full, but not 100% full. So you'd have a higher wire feed speed, but also you will have, because of this extra resistive heating, you're going to have a higher burn-off. This thing we're calculating here is the one I showed you from this very complex graph from ESAB's data. But this comes from this formula too. And this reason, this about 20% that we calculated, 20% increase in productivity, That's the main reason why people sell you metal core wires. But it kills me, because you could do that with an extended stick out. I don't know, why don't they sell extended stick outs? But you can calculate this. Now, in this case, I assume that the sheath is 60% of the area and the metal powder fills 60% of the inside. Oh, okay, here is this graph I showed you before, right? Okay, so if we look at 200 amps, it says 6 pounds an hour, right? So this is essentially 3 pounds an hour per 100 amps. And that's what we have, 3 pounds an hour per 100 amps. These numbers I'm giving you, which are not in any book, they're just waiting patiently until I write them. Nobody else has them. But you can do all these things. And you can do it for aluminum too, and you could do it for other metals too, at least in an approximate way. Effect of flux core. Flux core is funny. So if I have flux core, I can, if I have flux core, I have fluxes inside. So there are two things that happen. One is we have higher resistance, so we have more joule heating. But also, we're melting less metal. If we melt less metal, we can go faster. So flux core tends to run faster than MIG. No big news, everybody knew. But when you compare the pounds per hour, right, the deposition rate, the burn off, now it's more or less the same. Right? You're not any better. And the reason is the wire has less metal, right? So you move faster, you're more or less even. You have a higher joule heating, because, and that's good, but you need to, your enthalpy is higher than in MIG, because now you need to melt the fluxes, right? So here, for the sake of this graph, I'm assuming that melting the flux needs a 10% extra enthalpy. At this stage, me and you can do amazing calculations. I'll tell you what the next problem is. The companies don't want to tell you how much flux they put in, much less they're going to tell you what flux they put in, right? So it starts to get tricky to do these calculations. I will figure out what those numbers are, right? Because in the end, they give you these curves, so you can back calculate it somehow, right? So flux core, they can sell me metal core for the productivity. They cannot sell for the deposition rate. They cannot sell me flux core for the deposition rate. Now, flux core compared with MIG is kind of meh, but flux core compared to stick is awesome, right? And the competitor of flux core is not MIG, is stick. And flux core is amazing, right? Don't do stick. That's the bottom line. Okay, so this is what I wanted to show you about deposition rate, and how to calculate it. Do you guys have any questions? How deposition rate? Yeah.
Sorry, could you just clarify the two lines in one graph?
Okay. Blue line is 045. Okay, in all this graph, the blue line is MIG welding with 045 wire. MIG welding with 045 wire. And with a droplet, this condition. The red line is anything else I'm comparing with. In this case, I'm comparing it with flux core. So the red line is the burn off here and the wire feed speed for flux core.
And what are the differences? Is that the burn off on the right side, right?
Burn off is on the right. That is in pounds an hour, or kilograms per second or minute or whatever, right? Like what matters is let's know our science. On the left is wire feed speed. Any questions about this one? Okay, so this is going well, and we're moving faster than I thought. So this is what I'd like to do. We're going to have a seminar, and I'll do it. It's because it's the first time we teach concrete problems on this. If you wish, we can take a break now and start the seminar earlier and take whatever time we need for that. I have 2 problems in which I would like to do, but I would like you to do it, right? So that would give us time to do it properly.
Do we have the DBR today?
You have a DBR today and another DBR tomorrow, right? So today we're going to have the seminar. Those of you who ran out of opportunities for the DBR might need to go, right? Either way. So sounds like you ran out of excuses. Yeah. Okay, so let's do this. The DBR is at 3:30, right? So if we take, so what do you say we take a 10-minute break, and then we get started? At least you get to see a beginning. All right, let's take a 10-minute break, and we come back here at 3:10.